Hello, my name is Drew Rosno. This is case study 7, looking at MOSFETs in drones. For this case study, we are going to verify that the MOSFET is going to exceed the 125 degrees Celsius with that 15-second burst by running a transient simulation. Then we're going to make a redesign and ensuring that that gets below the 100 degrees Celsius for safety margin, as well as not adding more than 15 grams. For this simulation, I use silicone, which is what most MOSFETs are made out of. I researched the conductivity, specific heat, and mass density. Boundary conditions and loads, everything is selected by volume except for convection. So the initial temperature and heat power is all selected by volume. 300 Kelvin as the ambient temperature. That's also included in the convection. And for the convection, I selected all the exposed surfaces except the one that's going to be placed onto the chip. And the heat power, like I said, is going to be activated for 15 seconds and then off for 15 seconds. With this simulation, I got to 155 degrees Celsius roughly. Performing some validation with a MathCAD solve block, I got a value of 157 degrees Celsius. So comparing these two, we're in a percent error of around 2%. So I'm confident that my simulation is running as it should. For the redesign, I did an aluminum heat sink. I added fins to increase convection surface area. Even with free convection, um, it is helpful to cool the MOSFETs, and that added roughly 6.5 grams. With this redesign, I got to a max temp of 100 or 86.9 degrees Celsius. With this, I also decreased the convection coefficient to 5 to ensure that the redesign really would um, keep the MOSFET cool. And this is just comparing to the original baseline design. As you can see in this temperature over time graph, the redesign is under that 100 and has a slower rise, and the baseline has a higher rise, well over the 100. Next steps is to validate this with real world testing before launching worldwide. Thank you.